So let us start this class. So we have in the previous lectures we have seen how to take covariant derivatives of quantavariate vector and covariant vector and also tensors in general. So let us now consider the let us now write down the covariant derivative of the metric tensor, which is a tensor of type 0, 2. It's a covariant tensor of second order. So there are two indices. So this you can immediately write it down as this D C A G D minus gamma B C D. Okay. So you just write this down, and then you can also write down grad B C A is will be C A minus B C G C. Let me just comma B. We will already make here. B A G C. Is it okay? Then the last one, where A is equal to del A comma B. You just write down the three covariant derivatives in this form. Why I wrote down these three relations? If you note carefully, you will see that this is grad C GAB, and now you just use cyclically, you just replace the indices. So the next one is grad B, so B comes here, C goes here, A just shifts, and the next one is A, B, C. So it has been written in a cyclic form. And the important thing is that I shall demand that all these three are 0. And this condition that covariant derivative of the metric tensor is 0 is called metric compatibility. This condition is called metric compatibility. This is an important input in general theory of relativity, and one can actually show its connection with the equivalence principle. So if you take this, and now what you can do is just add these two up and subtract this from this result. If you do that, so if you add it and subtract this, then you can immediately see that some of the terms will cancel. So what we shall have is del C GAB plus del B GCA minus GBC. So you have added these two and subtracted this one. And then if you demand that this gamma DAB, this is symmetric in the lower indices, then these two terms will cancel. Because the metric tensor is obviously symmetric in the two indices, so this will cancel. And then you can also cancel other terms probably. Gamma D, GAC, GBD, so this will cancel with this one. And what else? Seems this cancels with this thing, and this will just add, right? Because you are adding these two, subtracting this one. This will not cancel. So this will add up. And since gamma DCB is the same as gamma DBC, so what we have is gamma D BC GT. This is what we have, and this is equal to 0. So from here, we can immediately write the following thing, that gamma D BC GBA is equal to half of del C. You can see this color. Is it okay? Fine. So this is a GAB plus del B BCA minus del A GBC. So this is what we have. And now what we can do is you can multiply this by GAE both sides. GEA and AE are same. So if you do that, then GAE and GDA, this will give us AA, so GD, gamma D, BC. Therefore, we can replace this by E. So gamma E BC is equal to this expression. So what we can see is that if you demand the metric compatibility relation, basically gives us the relation between gamma and the metric tensor, the connection and the metric tensor. So this is something very important. So you can write this down in a nice way. What you can do is, so gamma EBC is equal to this. So you can actually, so EBC of all are free indices. So you can actually replace E by A, and then this will be also A, and A was a dummy index, so you now just change it to D appropriately. You understand what I mean? Is it okay? Or should I write it down explicitly? See, what I am saying was, she's saying is the following. Gamma E BC is equal to what? Half G. What was this? Please tell me once more. G E A or A, whatever. And what was this? A, right? So gamma E, this is G E A del C G A B plus del B G C A G B C. So the first thing that we can do is A is a dummy index, so we can change this to D. Okay, since A is a dummy index, and now you can replace this index E by A. So you have a nice relation gamma ABC. Instead of EBC, you can write it down as gamma ABC, which is this. The important thing here is that The metric once you impose the metric compatibility relation, what it does is it fixes gamma, the Christoffel connection symbol, the connection that we had introduced to define the covariant derivative in terms of the metric tensor. So this is an important relation, and from here you can see, immediately that the entire expression, we had assumed one thing, that this was symmetric in the lower indices. So you can see from this relation that it is still symmetric, it must be symmetric. It should be consistent. So you can see the symmetry of this object. Just replace B and C, you will see that this expression is symmetric. Okay. So this condition you should remember this to be the metric compatibility relation. Okay, so let us proceed now from here. That's a minute.
You said that the affine connection is symmetric. Basically, affine connection is a property of manifold. So basically, it's so basically can be encountered manifold. Like
this is the Christoffel connection. It's a Christoffel connection.
So can it be possible that there is some manifold for which this affine connection?
There are examples, but see, we have not got to Einstein theory also, so we should not talk about Einstein-Cartan theory. There is much beyond. Einstein-Cartan theory will come. We are not aware, still not acquainted with Einstein theory. So Einstein-Cartan theory will, if you say, then we will not understand. But the thing is that, see, it is actually, what is general theory of relativity? Or why did Einstein name this as general theory of relativity and not a theory of gravity? He actually named it general theory of relativity because he understood that what he realized was that general theory of relativity, it is some sort of it is a generalization of the special theory of relativity, because at locally you will have special theory of relativity. That is why we named it general theory of relativity. But the point is that you can, and it turns out that the theory of gravity that you get out of general theory of relativity is some theory where this connection is actually, if you ask so many times, it will be a problematic thing. First of all, you are not coming in time, and then you are continuously disturbing the class. If you come late, that is not a problem, but then just enter the class. Okay, so the thing is that in general theory of relativity, you are considering from general theory of relativity, the gravity theory that you are getting deals or tells you that your connection must be a symmetric object. You don't need to. The observable gravity theory that you get, for that the connection is symmetric. So in general theory of relativity, that gives you the observable theory of gravity, considers manifolds which have the connections to be symmetric in the lower indices. But there can be other weird theories where you can have the connection where the connection does not have that property. So that is completely fine. But you have to argue that that particular theory is an observable theory of gravity. But so far you have not got Einstein's theory of gravity. The observations that you have in nature, Einstein's theory of gravity passes all those tests. So we are happy to work with connections which are symmetric so far. But now the advantage of calling this general theory of relativity, because you can formulate your own theory of gravity. That may not be an observable theory of gravity, but you can formulate your own theory where the connection is not symmetric. That is the thing. So for all the observable theories of gravity, you will have this problem. The thing that I mentioned is that, see, this relation that you get, how do you get this relation? This relation you get from metric compatibility. Metric compatibility is equivalent to the principle of equivalence. You can show that both are demanding metric compatibility is the same as demanding principle of equivalence or imposing the principle of equivalence. Huh? That is a, just take it for now. Or try to think how you can show. It's a good question that how, but you can show it. Metric compatibility, you also came a little bit late. So what I did today, so the thing was that we started out with this equation. This was the equation. First of all, we just wrote this down from our knowledge of writing down covariant derivatives. And then we wrote it cyclically, 3 equations. Then the physical input, this has nothing to do with mathematics. This is the mathematical part. Where is the physics? The right hand side is the physics. We demanded that this covariant derivative of the metric tensor is equal to 0. So when you demand this with metric compatibility, then you see that gamma gets connected to the metric tensor in this way. And since the metric tensor is symmetric, therefore gamma must be symmetric in the lower indices. So this is now I am saying that this metric compatibility is basically the physics input because you cannot get it from mathematics. So if this is the physics input, then the question arises is that it must be connected in some way with the equivalence principle, and you can indeed show that once you demand metric compatibility, you will get equivalence principle from here. Okay, so if this is okay with you, then let us do another. Let us introduce another derivative today, which will be important for later purposes. So once again, let us consider a curve gamma, which is parameterized by lambda. So in any arbitrary coordinate system, the coordinates here say lambda. Okay. So it is parameterized by this parameter lambda. This is point P, and this is point Q, the same as we did before. And this is say plus BXA. This point is Q. And let us consider a vector field here in the neighborhood of this curve gamma. And obviously, you can see we have already introduced this that UA is BXA lambda. Then UA is the tangent vector at any point on the curve gamma. Okay. So if we have this, then we can write this thing as x prime. Previously, we did not write it in this way, but now let us write it in this way. And you can interpret this equation as saying that you are going from some coordinate system xa to some coordinate system x prime. It's a way of interpreting this equation. 2 points which are infinitesimally close to each other. So one is xa, one is xa plus bxa, and this part we are calling x prime. So let us, we have already done this calculation earlier. When we introduce the covariant derivative, a at the point q is nothing but a at xa plus bxa. So this is, you can now make, please don't get confused because I am using this, these are arguments. You can use this as b equal to I or this b. This is x, then b. So this we had already calculated earlier. Since this is infinitesimal, so up to this order, up to dxp, this is this. Neglect the other terms. Now comes the important part that we have not done earlier. Let us do that now. So you are making a change of coordinate from xa to x prime. So x is being changed to x prime, and you know that under this coordinate change, a x is transformed as a prime is x prime, right? And what is the transformation property? The transformation property will be del x prime A, del x B, AB. And this is equal to del x B. X prime A is now xa plus dxa. This is equal to, the first term is del xa del xb, and this will be say dxa. And write this down as this term. What we can do is we can write this as dxa d lambda d lambda. But this is equal to u with d lambda. So what we have is plus this is UA, so delta xb, so this will be del UA lambda dx. So it's equal to this delta AB. Del xa del xb is delta AB. So you can now write this down as AA at x, and then we have plus del d UA d lambda AB. Is this okay? Obviously, you can see that A at Q and X prime is also Q, right? X prime is Q. X is what? P. Obviously, we can see that this object and this object, they're different. They're not equal. Right? They're not equal. You can see the structure. This is also P. Just X is, this point is P, X prime is Q. So we have replaced all these things. These two things are not equal. And now what we can do is we can define a derivative which is written in this way. You can write this as in this way, or you can also put a dash here, whatever you feel like. So this is U A P this is defined as AAQ is the definition. It is called the Lie derivative of the vector field AAP along the curve gamma.
Sir, the mobility derivative can be understood physically as just taking from Q to P and taking their difference. I mean,
Transporting it,
yeah. How to understand?
I'll tell you in a moment. But this is the, mind you, see, you will notice one important thing. These are all equalities, right? And sometimes I use this symbol. This means that this is defined as. This is defined as. This is not an equality. You define it like that, and this is called the v derivative of this vector field along the curve gamma.
Derivative along the vector A at point P.
It is that is why it is defined. It is at Q. That is why I am saying that it is defined as. The definition is like that. This is my construction. I am saying the Lie derivative at the point P is basically the function, the Lie derivative of the vector field at Q minus this in this way, and to show Holmes' question that what is the meaning? If you see very carefully, then you will find something interesting. This is what is the same point, right? So the argument is not changing. What is changing is the functional form. So Lie derivative is basically the functional change. The change in the function at the same point. This is something very important. You should remember this. This is the change in the function at the same point.
At P, its derivative is changing Q.
That is what I am saying. It is defined in that way. The question that Anirban was asking, that he was also having this confusion that here I am writing P, why I am writing Q here? But this is my definition. This is the way I construct the derivative. Okay. So if you take this definition and then nothing, you don't need to do anything else. The thing is already. So what is AAQ? AAQ is AAP plus this thing minus A prime AQ. What is this? AAP. So this term and this term will cancel. And from here you will find that this is del B AAP. Now you see the P is coming here. Minus del B UA AAP, and both will be just
The second term index, upper index of ABP.
Let me just now I have to do one more thing. What I am doing is del B AAP, but I have not written down the full thing. That is why there is an error. So what I will do is I will write this down as d lambda into d lambda, right? I will write this down. This was just dxb, so I will write it as d lambda d lambda. This is ub, so I have to write a ub here. And then you see d lambda and d lambda. So d lambda is common divided by d lambda. So that gets cancelled. So you don't need to take the limit anymore. So Lie derivative. So let me write down the final result. The final result is.
So that should be AB in second term.
Correct. I will just check it. So this will be del B UA. This is B. And Q values B. So what we have is LU AA X. So now you can replace P by X. That is now, you can see that P has come in, right? So the thing is that it has been constructed in an intelligent way so that P again appears. So P is appearing on both sides now, so you should not have confusion. And the result is UV del P AA at X minus AB del B. So this is the Lie derivative. So we have now investigated or studied two different kinds of derivatives. One is the covariant derivative, the other is the Lie derivative. And in case of a Lie derivative, you can see that this is a more primitive operation than covariant derivative because it does not require the notion of connection. Connection is not required. to define this derivative. In the earlier case, you needed a connection so that it transforms in a covariant way. But here, you define it in such a way the connection is a nice operation, it's a Lie operation or Lie transport. So here you don't require any sort of a connection. But the interesting thing is that you can actually bring in the connection here by replacing the ordinary derivative by the covariant derivative, and I leave it to you to check. You just expand it, and you see that the connection terms will fall out, will cancel. You can actually replace them by covariant derivatives. And as I mentioned in the previous lecture also, that your derivatives should have the nice property of following Leibniz rule. So you can all these derivative operators they obey the Leibniz rule. So I will leave it as an exercise for you to do it, and you tell me in the next class. It is important that what about this? I'm taking a tensor of type 1, 1. So it has one contravariant index, one covariant index. What is the Lie derivative of this thing? Can you calculate this? So I give it as an exercise to you. Please do it. And you can generalize this for other things also. You should be able to do it. Okay. Do you have any questions at this point? Physically, so far you just this is a mathematical of this completely mathematical. But how it is used in physics, that is a separate issue. We'll see how you can use it in physics. The derivative and whatever. You can have some sort of a physical idea about this physical notion, even coming out from this mathematical thing that it is this derivative is a sort of a functional change. Because only the functions change here, the forms. The point functional change at the same point. So that is what at this stage you can say only this much, not more. I just wanted to introduce this because I wanted to show you at least two differentiation operations on a manifold. So we have learned what covariant derivative is, and you know what is the physical significance, because everything should equations here, whatever equations you write in general relativity or in physics, they should be general coordinate transformation, they should be covariant under general coordinate transformation. That is why we needed to introduce this covariant derivative operator. That was from the demand of physics. But this, so far, we have no such thing as what should be its connection with physics. It's something mathematical. Let us introduce it, and this is the form of that. So now we shall straight away come to geodesic equation. So if you have any doubts, so far what I would like to know is that are you following the mathematics, the mathematical part? What the junior students, are you okay with it? Is it okay for all of you? You are following everything, right? If you don't follow a step, please ask me. So the next topic that I would like to discuss is geodesic equation. So in flat space, you know what is the equation of motion in flat space of a particle in flat space time? Huh? Shout please. Well, V2 tau 2 for free particle. I'm asking for free particle. So this is reasonable in flat space. This is a reasonable equation of motion for a free particle. But now we would like to generalize this differential equation in curved space-time. So what would be a natural generalization of this? Huh? So mass is free particle. Mass has it's a free particle. So on that side there is nothing. So the mass is cancelled. It is called considered massive particles for the time being. That is why see there is an important thing. Since these are massive particles, that is why you can consider differentiating it with respect to the proper time. For massless particles, proper time is 0. So that is a different issue. There to be that is a little bit tricky to do. But so far, what we are considering is massive particles for which the proper time is not 0, and in flat space-time this is 0. So how will you generalize it to curved space-time? What would be a natural generalization of this?
To find the derivatives, and check, generalize the derivatives such way that in flat space-time this equation comes.
In flat space-time, this equation comes. That is true. We have to generalize it in some way. So in flat space-time, it will come like this. But suppose in locally flat Cartesian coordinate system, the equation is basically this thing, right? So this is the simplest equation that you can consider in curved space-time. You have something in flat space-time like this, and you can say that this is my equation in a locally Cartesian coordinate system. So that would be a generalization of this equation. Let's see what happens if you consider this equation. So let us make a general coordinate transformation. So from now on, I will write general coordinate transformation as GCT. This is an abbreviation for GC, general coordinate transformation. So let us make a general coordinate transformation. Let us transform XA to X prime. So XA this was tau. X prime means X. We have made a general coordinate transformation, and under this dxa d tau will transform to dx prime d tau. Okay, and this we can write it down as right general. So how will this transform? This is basically the equation. Let us see how will this transform. This is basically d tau. This is d tau 2 prime that is equal to d tau of dx prime. And dx prime d tau is this. This is dxd d tau. This is ub. So you can write this as d tau. This is this is a tangent vector. Let us now calculate this. It's simple to calculate. The first term is del x prime a, del x b, and d tau acts on this one. So this is d ub tau, first term. And the second term is this acts on this, ub remains. So we have d tau Okay. And therefore, V2 XA B tau 2 under GCT goes to V2 X prime A B tau 2 equal to the first term is del X prime A del X B. QB is what? BSB d tau. So this is B2 XB b tau 2. Okay, this is the first term. The second term is plus, just make a derivative. Again, apply the same rule. This will be del 2 x prime a del xc del xb, and then you have to just get dxc d tau. So this will be dxc d tau dxc. Is this okay? So we can immediately see that if we demand this to be the equation in curved spacetime for a free particle, then this equation, which is completely valid in flat spacetime, there's no problem with this equation. But if you demand that that same equation remains valid in curved spacetime also, then this particular equation does not transform in a covariant way. Because this equation goes to under GCT, this will be then equal to 0. But you can see that the covariant structure is spoiled, does not transform in a covariant because of this term. In curved spacetime, you cannot generalize the equation like this in a simple way. It's lost. So what to do? We already know what was the transformation. So in the previous lecture, we have derived the transformation of the Christoffel connection, right? Which is symmetric in the lower indices. And let me just write down the transformation. So this was gamma A, this is X under general coordinate transformation. This goes to gamma A, B, C, X prime, and that is simple to write. This was del X prime A. You just see what the indices I have used A1. A1 del X B1 del X prime B del X C1 del X prime C, then gamma A1 B1 C1. So this was completely fine, right? This was completely transforming in a covariant way, in a tensorial way. But then there was a problem. The other part, which was not transforming in a tensorial way. So that term was minus. Please check whether it was minus or plus.
Minus.
It was minus. Very good. This was very good. Prime A del X B1 del X C1 del X C1 by B del X B1. C1 by B, this is C. Okay. So we have now written down this part. Fine. So this was the transformation that we derived in the previous class. Now let us do one thing with this. Let us see gamma A B C. Let us multiply this by this. Okay. So we had this transformation. Now we are multiplying by factors of UP and UC. Under general coordinate transformation, this will transform to gamma A B C x. This will go to x prime. Then we will have dx prime b dou. So this transforms like this. And we know how does this transform? That we have written down just now. So let us just, okay. So I will not write this one again. If you wish to write it down, you can write it down in your notebooks. So what I will do is, I will just multiply this by these two factors. We have these two factors. And what are these? These are basically, I can write it down as del x prime b, del x b1, dx b1, tau. You see the index used e. Good. So this, and then I'm writing it over here. So, and then here this term, this is del x prime c del x e1 dx e1. I'll use the transformations of those values. So this under GCT transforms like this, and this is equal to this thing. Now what we need to do is just multiply this with this. Please do the multiplication yourselves. You get two terms, del x prime a, del x a1, and so let me just write it down. So this will be del x prime a, del x a1. Then we have del x b1, del x prime b, del x prime b, so that will get cancelled, right? Del x prime b, del x prime b will get cancelled. And what we will have is del x b1, del x b1. So we will have delta b1 and b1 from the multiplication of this with this. And then you have a dx d1 d tau. Dx d1 d tau will now become dx d1 d tau. And then you can get rid of this Kronecker delta. Right? Now this is del x c. Once again, del x prime c, del x prime c will get cancelled, and you will have a Kronecker delta, delta c1 e1, and then you have a dx1 dx e1 d tau. Dx e1 d tau will become dx c1 d tau, and you can get rid of this Kronecker delta. So the first multiplication is done, and then you have the second multiplication. So let me just write here dx e1 d tau dx. So did you do the other multiplication? Is it done or should I do it? Huh? Gamma will be there, sorry. Thank you. A1, B1, C1. Is it fine now? The first term is right? Now what about the second term? So if you multiply, get something out of it. Del x prime C. Okay. So let us do it. Minus del 2 C1 del x C1 del x prime B. So this and this will get cancelled. So this will be giving us delta C1 D1. Right? So your dx d1 is this. So this will be again dx c1 beta. And what about the last term? v1 e1. So dx d1. Did I miss anything? Please check. I think I have not missed anything. Is this okay? So now I am just rubbing this part out because you don't need this part. From here, you can immediately see that dx d1, dx c1 is a common. You can take them out. Therefore, you can write this as del x prime a del x a1 gamma a1 a1 c1 x minus b. Once we have this, we now take the following combination. Where should I write? Remove this one because I want to keep this. This is important. Let us now take the following combination. Let us take this combination and this under GCT. We go to G2 prime A, beta 2 plus gamma times A BC x prime dx prime B beta. Okay, this is simple. Everything, this particular expression under GCT will go like this. And we have calculated the transformation properties of both this thing, this object, as well as this object. So let us just put it down. If you put it down, you will see that this will d2x prime and beta 2 that goes as this thing, lx prime a. Let me just write this as del x prime a del x b del 2 plus. I'm not writing this down. This is this term, right? And the next term, this transforms like this, and this we had already calculated. This was this thing, right? So we just add it here. So if you add it, what you will get is del x times a del x a 1 comma a1 b1 c1 x. So this is the first term, this multiplied by this, and then we have a second term here, minus del 2 this, that I am writing down as again one dotted term. And if you look at carefully the dotted terms, then you can see that this and this one they cancel each other. Just look at this term and this term. B1 and C1 are dummy indices, so you can replace this by CB, so CB, so they cancel each other. Okay? And therefore, you can see that this object transforms like this, and that is equal to, from here, you can now remove these parts. So this is now equal to del x prime a del xp equal to plus I have replaced A1 is a dummy index, so I have replaced it. Let us replace it by this A1 here. This A1. So replace A1 by B now. So if you do that, that is B and B1, C1 are already there. So you can replace it by CG, DX, C. Okay. And now you can see that this object was not transforming covariantly, but this combination transforms perfectly in a fine covariant way, because you can see that here this particular object, if the free index is only A, so there is only one free index, so it should transform like this. Therefore, this is a covariant transformation, and you want your equation of motion to transform in a covariant way, and therefore you say that this thing is the equation of motion of a free particle in curved space, rather than this thing. We were earlier considering this thing. We saw that this does not transform in a covariant way, but this thing plus this thing transforms in a covariant way under general coordinate transformation, and therefore this thing is equal to 0 is the equation of motion for the free particle in the curved space. And this is known as the geodesic equation of the particle. So this basically physically tells you that if you have a free particle moving in a curved spacetime, the curved nature of the spacetime basically tells the particle how to move in that curved geometry. And it is, you can understand it in this way, it is the straightest path joining two points traversed by a free particle in a curved spacetime. It is not really a straight path. In flat spacetime, it is a straight line, but in curved spacetime, it is the quote-unquote straightest path that you can have that a free particle will traverse in a curved geometry. Okay. Do you have any questions at this point?
So how to show that the path will be a geodesic? I mean,
This is called a geodesic equation.
So I am saying that in extension of geodesy, that arc of the great ellipse.
That you are taking a particular example. So you will work out what by taking an example. This equation basically determines the trajectory of a free particle in a curved space. You can say that this is only a free particle. But when we learn in ordinary physics, in special theory of relativity or in non-relativistic physics, we are not really interested in free particles, right? Free particles is trivial, but you can see that in curved spacetime, even finding the equation of motion for a free particle is quite involved. And the equation of motion is this, and it is actually interesting. How will a particle which is free from any interactions move in a curved spacetime? If you just keep it in a curved spacetime, how will it move? Okay, so now we will write this equation in a different way. This is the geodesic equation. Let me just write it down here. This is geodesic equation. Let us write it in a nice way. We have introduced the following. Right? We have introduced the following. dx and deta. So you can write this equation like this. This is dqa tau plus gamma a bc to 0.
Please change the color of the chalk.
All the chalks are really there. They're not writing it. Can you see this? This is clear. I will not use blue. বলো কি বলছো বলো Rajmula? Huh? No, if you have any question, you can ask. Feel free. Just as I gave you the permission to enter freely in the class without asking me. I'll ask. Please ask. You know, in this kind of serious classes, you should sometimes throw things like this. So this will make it more. The class will be more cheerful. Sometimes you should throw things like this. The Joyce is already a colorful character. Colorful boy. Okay. So you can see that this equation, you can write it in this way. And now, what we can do is the following. You can write this as how can I write this equation? It will be Excellent. Who is asking the question? Shoham. Okay, I will take your question. Just a minute. I want to write this in a nice form.
You can write it in terms of covariant relation.
That is what I am trying to do.
Just EXVD
Good. So I will just write it this way. This particular term, I will write it as del UA. Very good. Del XB. Option number 2, DHB out plus gamma A BC UB UC. Now this is replaced by UB. What we can write now is del UA B plus gamma A BC UC UV. Okay? But this is what? This is nothing but covariant derivative UA, right? So UV covariant derivative UA, if you remember, I introduced this notation. Capital D vector field, small d tau is basically UV grad the UA. So you can
small d lambda.
Lambda was the parameter of the path. Tau is the parameter of the path.
yeah, let me just check. It was how did I write it down? No, this will be dd tau. This is fine. It's not a problem. You are parameterizing the curve by tau this time. So earlier it was being parameterized by lambda. Now you are parameterizing it by tau, by the proper time for massive particles. For massless particles, you cannot parameterize it by tau with the proper time. You have to parameterize it with a different parameter. Now George will ask how. Next question is how. But so far, let us discuss massive particles. I will come to the massless particles. So what you can see from here, the geodesic equation is basically this: UB grad B UA is equal to 0. Now let us come back to covariant differentiation once again. You remember how we did the calculation of transporting the vector from one point to the point where we want to take the derivative. And there, if you remember, we had written it down for a general vector, right? For an arbitrary vector field, AA, and that was what? UB, Nabla B. So this is sometimes called Nabla or grad. This was the expression, right? This was the thing that we calculated, and there George was asking an interesting question, which I did not answer at that time. He was saying, or rather, he was commenting that you are parallel transporting it. But I said that you have just transported it. Now, if you look closely at this equation and you apply this equation for this tangent vector to the curve. So you have a curve gamma, and at this point xa lambda, which is parameterized by tau say now at the proper time. This is the tangent vector at this point P on the curve, which has coordinates xa tau in any arbitrary coordinate system. So if you apply this equation for the covariant derivative for this tangent vector, then what we shall get?
Small d was capital D.
Accident. What?
Denominator D.
So the equation that we derived from geometry for covariant derivative, we are applying it to the tangent vector to the curve. And in flat space time, we know in Euclidean geometry, we know that if you have a straight line, what is a straight line? A straight line is one which carries its tangent along itself throughout the path, throughout the straight line. So you can generalize this idea to curved space-time or curved spaces also, curved geometry. You can say that the straightest path in a curved geometry is the one which carries its tangent parallel to itself. The straightest path in a curved geometry, and that is what? That is the geodesy. It's the geodesy. It is the one which carries its tangent parallel to itself. You are just generalizing the notion in ordinary Euclidean geometry, where we have the notion that a straight line is one which carries its tangent along itself throughout. We have generalized it, and if you generalize it, then you can see that this is the tangent vector, and the straightest path in curved geometry is what? One which carries its tangent. So straightest path means it is the geodesy. That is equal to 0. And that means what? You have transported the vector parallel to itself. So this condition, when you are equating it to 0, this is actually really the parallel transport condition. You have parallel transported the vector along the path. So geodesic is one where you have actually transported the tangent vector parallel to itself along the curve. So in this way, also you can understand the equation of the geodesy. That is why I wrote down it in a nice covariant form, in this form, and this is equal to 0. This is a geodesic equation, and this was the condition for covariant derivative. I equate it to 0 for you take the write it down for a tangent vector. Equate it to 0, it means you have parallel transported the tangent vector.
So, sir, if basically means along the geodesy, there are 2 points A and Q, and I parallelly take AQ to AP, then those 2 vectors will be identical.
Along the geodesy.
Along the geodesy.
So we have derived the geodesic equation now in 2 different ways. If you look closely, we have actually derived the geodesic equation in 2 different ways. One was by demanding the principle of general coordinate transformation, that the equation should remain covariant under general coordinate transformation. In this way, we have derived the geodesic equation, and in the second way is by a notion of parallel transport. If you parallel transport the tangent vector along a path, then this should be equal to 0, and that is the geodesic equation. So the geodesic equation is like the straightest path in a curved manifold because you have transported it in a parallel way. And why straightest path? Because straight line, you know, the tangent is always parallel. So we have already derived it in 2 different ways, the geodesic equation. Let us now do it in a third way. We will do it in 4 different ways. So already 2 different ways are done. We derive it 2 more ways. The important thing is that, as you were asking, about some trajectory in some along the leaps or whatever. The important thing is that, see, from the geodesic equation, now you can really calculate the trajectories of any free particle, right? If I give you the geometry, then what you can do? You can calculate the metric components. You can calculate it, and Christoffel connection, they are connected to the metric tensor. You can calculate it. You put it in the equation. You will get a set of differential equations. Solve those differential equations. You will get the trajectory of the particle in the free particle in the curved space. So let us now, as we all know that we always try to understand any particular equation of motion from a variational principle. So let us now do it from a variational calculus approach. And let us consider two paths, 2 points in the curved manifold, and let tau AB, be the proper time taken by a particle in going from A to B. A and B are 2 points in the curve. This is A and this is B. These are 2 points, and let tau AB be the proper time taken by a free particle to move from here to B. Okay. What will be that? Integrated form. But you know that this is invariant under general coordinate transformations. Okay. So if you set C to be equal to 1, you can do it. You can also keep C. That is not very difficult task to do. Then what we shall have is the following. There. Let's divide by lambda, lambda. Then this will be lambda. Okay, 2 d lambdas, d lambda into d lambda. And if you now take a square root of this, then this will be equal to this. So the curve xa along with the free particle moves in the curved space-time is parameterized by an invariant parameter lambda. That is why we have, so tau was the proper time, and now we have changed it to an invariant parameter lambda. Okay. So you can see that this is like an action, right? You can interpret this as the Lagrangian and this as the time LDT kind of thing. So this is like an action. And what is the principle in classical mechanics? That if you extremize the action, then you should get the classical equations of motion. So we shall do the same thing here. We shall try to extremize this particular object. But before doing that, I shall do one more thing. Suppose I make a transformation, the invariant parameter that you have, which parameterizes the curve. I replace lambda by some function psi, where psi is function of lambda. Okay. So I do this replacement. Then what will happen to dxa d lambda? Dxa d lambda will go to dxa d psi. And dxa d psi, once again we have to apply chain rule. by the chain rule. Fine. Now, under this reparameterization, so I call this my reparameterization. My parameter by which I was parameterizing the curve was lambda. Now I am reparameterizing the curve by a new parameter psi. This is a function of the old parameterization lambda. Under this reparameterization, tau AB, we go to tau prime AB, and that will be equal to B. Okay. Under this reparameterization, tau AB goes to tau prime AB, that is equal to this. Now, tau prime AB is equal to integral A to B. What is desired? Or this you can write it down as what? dxa desired is. So this should be GAB. dxa desired is this. dxa yeah. D lambda desired. dxb this is dxb d lambda desired square root desired. Okay. Now d lambda desired you can take outside. Nothing but this. Okay. So what does this tell us? Invariant. So this tells us that this action that you have is invariant under reparameterization. So this symmetry, it enjoys a symmetry. It is called the reparameterization symmetry. This is something very important that you have. It's called the reparameterization symmetry. So you can parameterize the curve by any parameter that you like, but the action will be invariant. That is what you want to have. It's called reparameterization symmetry, and this particular symmetry is basically the guiding principle in writing down actions for other objects also. For example, a string and higher dimensional objects. So this is for a point particle moving in a curved geometry, and this is the same principle that is used for writing down the action of strings also, strings and membranes, whatever you have. So there also you have this reparameterization symmetry, and the action has a very similar form. You write it down in this square root form. This is actually called the Nambu-Goto form. This is called the Nambu-Goto. It's called the Nambu-Goto action for a point particle. But Nambu and Goto actually gave this action for a string. And why the important thing about this action, or you can say that this is a bad thing also, in some sense, because you have a square root. The square root is sometimes problematic. Problematic in the sense because with action, you may sometimes try to do path integrals. You may put it inside path integral, and then this particular square root can create problems. So it is not a very good thing. But then there are ways to write down different actions, and you can circumvent the problem of this square root. the important thing is that the guiding principle is that whatever action you write down for a point particle or high dimension of objects, it should have this reparameterization invariance. Otherwise, your theory is not good. This is something very. This should be your guiding principle in writing down some action. Okay, so we have shown the reparameterization invariance, but there are many consequences also of this reparameterization invariance. For example, you can this is a free particle, and you can try to calculate. See, this is the Lagrangian, right? This is the Lagrangian. So what should you do with a Lagrangian in classical mechanics? Before that, momentum. Canonically conjugate momentum. You have to calculate. So you can calculate the momentum. Once you calculate the momentum, what will you do? Hamiltonian. So please calculate the Hamiltonian from this Lagrange. It's a homework. And tell me what is the answer. Calculate the momentum and calculate the Hamiltonian and see what you get. So this is a problem that I leave it as an exercise. Calculate P and calculate H and see what you get from here. Okay. Now the important point that we have from this discussion is that since this action has a reparameterization invariance, therefore what we can do is we can choose a particular gauge. So it was written in terms of lambda, but now you know that it is invariant under any parameterization, right? So choose a particular gauge, lambda is equal to tau, because it is reparameterization invariant. And let us vary the action. So if you vary the action, to obtain delta tau Vd, that will be equal to B, and you have you have that Lagrangian, so it is basically delta of L, right? Delta of L. So it will be what? 1 by 2 square root. Here we have
That will be tau.
lambda will be tau because of so what it says that is that even if you parameterize it by lambda, even if the curve is parameterized by lambda, then also you can go to the proper time. That is why that is what the reparameterization invariance ensures us. So dxa b tau, dxt b tau plus gab twice of b tau y2, because it is symmetric, we will get two terms from the variation. So dxa b lambda, I have written it in this way. Another thing is that remember what d tau was. This is also important. D tau was square root, right? So this was GAB dxa d lambda dxd d lambda square root d lambda, right? This was d tau, right? Like this. So this particular thing that you have is nothing but d tau d lambda. This particular root থাকবে না? Excellent. Right, root থাকবে. Fine. Doesn't matter. Because tau is equal to lambda gauge. That factor is something. That is what I wanted to show. So if this is fine, what we have is tau by 2 times this. Now this is equal to delta GAB, that I will write it down as it's better to use UA into V plus twice GAB delta XC del C GAB dXA DHB delta XC. Here, what I shall do is the following. This term, I'll write it down in a different way. It the factorial. Okay. So what I will do is let's half, then this will come. Good. So now what I shall do is write this as GD tau of GAB DXA tau B minus G tau GAB write it in this. It's a total derivative. So I'll get two terms from there, and this term, the first term, if you integrate over tau, is a total derivative. Just demand that delta XB at the endpoints are same, so it will, or it is fixed, it is 0. So then, so delta is so what you have to demand is delta XB at A is equal to delta XB B. So the endpoints are fixed. There are no variations. Variations are not allowed. That is what you do in classical mechanics. Then what happens is this term goes to 0. This term is 1. Therefore, what we have is the first term, this term, and this term. only two terms. So this is the standard condition that we impose in classical mechanics. So variations are gone at new points. So this is gone. And what we have is minus tau GAB Please note this condition down. You are going to important. And now from here you will get two terms. I'm keeping the minus sign, so what you will have is minus GAB V2XA tau 2 delta XP is the first term, and then the second term is dd tau acting on this. So this will be d, or you can write this as del XC GAB dxc d tau. dxc d tau dxa d tau delta XC. So you have two terms coming out of there. So let us say which one?
Sir, for the first term, GAB is A and B are operating.
Which one? This one, no?
First term. GAB, A and B should be lower.
Right. Thank you. Definitely lower in this color. Very good. Downstairs. And have I made any other mistake? I mean, I have taken the minus sign. What will be minus? Let me just check with my calculation. Okay, I have an overall minus sign. But at the end, it is not the relative sign is obviously important, because what I shall do is I shall impose the principle of least action. The least action principle. Once again, you have to impose this imposition of principles, physical principles. This is the physics input. So if you impose, so if I can take this minus sign outside, right? So I can, what I can do is I can make this plus, and this one minus. Okay. So what we have finally is the following. And George for this. This must be downstairs. You're upstairs. So if you have made errors in your notebook while writing down, please correct this one. So this is 0 is equal to integral a to b. Now I will write down the terms. So this is g a b delta x b. So what I shall do is I shall make this c and this also c.
It will be the distance.
Yes, that is what I am trying to show. So this will be what I will make c. Just make b. So this is b. This is b. I'll make it c. C. Okay. So all these dummy changes we have made, and from here we will get g a c b2 x a tau 2 first term. Then we will have this term plus del del b g c dxa tau out is done. Then we have a minus R, and then C, and C is B. For an arbitrary variation, we have this. By imposing the principle of least fraction, you can see that for an arbitrary variation, the only way this integral can be 0 is that the integrand itself is equal to 0. Huh?
dx beta or dx beta.
Just a minute.
Last
Let me just check once more. Let me just check this, whether I written it correctly or not. এটার সাথে বলছো তো এখানে just put the appropriate factors. Put the there will be factors. Correct. This will be the dxa beta and dxb beta. Very good. Has to be
overall একটা beta.
overall একটা
Beta.
overall একটা না overall একটা beta তো আছে এটা তো আছে এটা তো আছে. So this is equal to 0, and from here therefore this is equal to 0. And now what you have to show is you have to show that you can cast this part in a Christoffel connection loop. That I leave it as an exercise for you to do. Please do it. This is the equation of motion that you get, and now you have to write it in the, because you know the final form what it should be. Please write it down in that form. So since these are dx and dxb, so what you can do is you can change this to b, change this to b. So then del b gsc minus half del c gab whole multiplied by dx d tau dxb d tau, you can take it outside, and then you can adjust the factors appropriately. Is it fine? Please do this, and from here the equation that you will get is the geodesic equation. So this is the third way of deriving this equation. From here, from the equivalence principle, I will show in the next class how to derive it from the equivalence principle. But the important thing is that you can ask the question that how many degrees of freedom are there for this free particle? What are the number of degrees of freedom for this free particle moving in this curved spacetime, curved geometry? Can you tell? Huh? 4. Are you sure? Huh? What are the number of degrees of freedom of this particle? Good, right. It's not 4, it is 3. Why?
Because it is due to movement, I mean, it's in 4D and there is a constant.
There is a constant. What is the constant? I have derived it for you.
It can move along this geodesy.
No, the constant is the following, that d tau d lambda is equal to square root of gab dx, that thing.
Parameterization is the constant.
Reparametration, but how do you get the constant? Precisely, it is d tau d lambda is 1, because we fix the case, d tau d lambda is 1. So 1 is equal to gab ua ub. So that is the constant. So it seems that there are four degrees of freedom, but there is one constant. Therefore, there are actually 3 degrees of freedom. Because you have d tau d lambda, that is equal to square root of that thing, gab dxa d tau dxb d tau. Those are ua ub. So gab ua ub is equal to 1. So that is a constant. relation. And therefore, out of the 4 degrees of freedom, 1 gets cancelled due to the constant, so you have 3 degrees of freedom. So it is everything is constant. That is what it should be. So in the next lecture, what we shall do is we shall try to derive the same equation, geodesic division equation, geodesic equation from the principle of equivalence and see how we can do it. So if you have questions at this point, please you can ask it. It's time for questions. Let us take some questions. So today the takeaway message is that we have learned what covariant differentiation is. How do you transport a vector from one point to another point? We have understood what Lie derivative is. How do you take the Lie derivative of the particular tensorial field that we have understood? Then we have employed the principle of general coordinate or general covariance. So under the general coordinate transformation, if you demand that, we have tried to obtain the equation of motion for a free particle moving in a curved geometry, and we have obtained that equation of motion, and that is called the geodesic equation. And then we have also derived the geodesic equation for that particle by imposing the concept of the straightest path in a curved manifold, connecting 2 points in a curved geometry. And there we have to incorporate the idea of parallel transport. So if you do that, you will straight away get the geodesic equation. And the third way we have understood is from a variational principle calculation by the standard way in which we do it in classical mechanics. So if you impose the principle of distraction, you will get the equation of motion for the free particle. So these are the things that we have done in this lecture. So if you do not have any more questions, so let us stop here for today.
Sir,
Huh.